Hi guys, this is A2 Chemistry, Organic Chemistry, and we're looking at drug synthesis. Question 1. Acebutolol is a drug that can be used to lower blood pressure, and the structure is given. Give the full name of the circled functional groups labeled P, Q, and R in acebutolol. So the functional group P is a C double bond O group next to an NH group. This is known as an amide group. Next, we have Q, in which we've got a C double bond O attached to two different alkyl groups. So this is what is referred to as a ketone. And R is a carbon atom with two alkyl groups, an OH group. And since this is skeletal formula, the fourth bond on the carbon atom would be a hydrogen. So it's a carbon atom with two R groups, a hydrogen and an OH group, making it a secondary alcohol. On the diagram of acebutolol below, draw a circle around any chiral carbon atom. So a chiral carbon atom is a carbon atom that forms four single bonds with four different groups on it. So if we start from left to right, we've got a CH3 group, a CH2 group, a CH2 group. Then we move on to the CH3 group attached to the oxygen, which is attached to the benzene ring. Then we move on to the secondary alcohol group. Here we can see that there are two different R groups attached to the carbon atom, an OH group attached and a hydrogen attached. So this carbon atom is a chiral carbon because it has got four different groups attached to it. Moving on, we've got another CH2 group, then an NH, then a CH group attached to two CH3. So this is the only carbon atom with four different groups attached to it, making it the only chiral carbon atom present in acebutolol. On warming with dilute hydrochloric acid, acebutolol splits to form two molecules. So warming with dilute hydrochloric acid means we are subjecting it to acid hydrolysis. So the question asks, draw a line through the bond broken by heating with dilute hydrochloric acid. So the bonds that are broken on heating with dilute hydrochloric acid, or we can say that by acid hydrolysis, are ester and amide bonds. There are no ester bonds present in acebutolol, but there is an amide bond present. So the amide bond is the one that will be broken. Draw the structure of the smaller molecule produced by this reaction. So the smaller molecule would be the one on the left. So that would be CH3, then CH2, CH2, C double bond O, and this would be converted into a carboxylic acid on acid hydrolysis. So we attach an OH to the remaining bond on the carbon atom. So this compound would be 1, 2, 3, and 4. So this should be butanoic acid. Suggest what would be observed when acebutolol reacts with the following reagents. If no reaction would take place, write none in the table below. So alkaline iodine solution reacts with a CH3 group next to a C bonded to an oxygen atom. So we have got this group present in acebutolol. So this would give a positive result. So the observation would be yellow precipitate. Universal indicator solution. Now, acebutolol has an NH group next to the secondary alcohol group, as we had already seen. So that NH group results in acebutolol being alkaline in nature, and the color of the universal indicator under alkaline conditions is blue. So blue color observed. This could be purple as well. It could be blue, it could be purple. But both of these colors are present in the alkaline region. Next is 2,4-dinitrophenyl hydrazine is a test for the presence of the carbonyl group. We have got one of the functional groups present in acebutolol being ketone. So this would also give a positive result. So we will have a yellow, orange, precipitate being formed. And Tollens reagent. Tollens reagent is a test for the aldehyde group. So there is no aldehyde group present in ace-butylol. So Tollens reagent will not give any observation. So the question says write none. So we are going to write none in this cell of the table. Butanoic acid can be reduced to form compound N. Compound N reacts with sodium. Suggest a suitable reducing agent for this reaction. A reducing agent that reduces a carboxylic acid is LiAlH4, and a carboxylic acid is reduced to an alcohol. So if we have butanoic acid can be reduced to form compound N. So butanoic acid will be reduced to form a compound N, which would be butane 1 all. So this would be CH3, CH2, 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 OH, which would be drawn as in the skeletal form like this: 1, 2, 3, and 4 carbon atoms with the OH group attached to the first carbon atom. And the question says draw the skeletal formula of an isomer of N that exists as a pair of optical isomers. So we need to convert this into an isomer. So what we have drawn here is the butane 1 all, the actual alcohol that forms when butanoic acid is reduced. So now we need to convert this into an isomer that has optical isomer. That means we have to convert into a chiral carbon atom. So for that, we will place the OH group away from the first carbon atom and onto the second carbon atom. By doing so, we end up with a molecule in which we've got a CH3 group on one end, OH on the other, H on the third bond, and a CH2 and a CH3 on the fourth bond, making this a chiral carbon atom to which the OH group is attached, and finally converting it into its skeletal formula. So 1, 2, 3, 4, and on the second carbon atom, we attach the OH group. And the numbering for this would be 1, 2, 3, and 4. And this skeletal formula is of butane 2-ol, which would exist as a pair of optical isomers. Another isomer of N does not react with acidified dichromate 6 solution but does react with sodium. So the OH group is present. Draw the structure of this isomer. So if it does not react with acidified dichromate, that means it does not undergo oxidation and it is an alcohol. So primary alcohols are oxidized to aldehydes, which are further oxidized to carboxylic acids. Secondary alcohols are oxidized to ketones, and tertiary alcohols do not undergo oxidation. So this isomer is a tertiary alcohol. So in order for this to be a tertiary alcohol, we should have an OH group present on a carbon atom to which 3 alkyl groups are attached. So in a compound in which there are 4 carbon atoms present, we end up with a compound called 2-methyl propane 2-ol, which would be the isomer that does not undergo oxidation. This is its displayed formula, and in order to draw its skeletal formula, we make the OH group here. So both types of formula have been drawn for the tertiary alcohol that does not undergo oxidation, which is also an isomer of N. Question 2. Ibuprofen and paracetamol are pain relief drugs. The structures have been shown. Ibuprofen and paracetamol both contain the aryl benzene functional group. Name the other functional groups present in each molecule. So we have ibuprofen having the COOH group as circled on its structure, And we have the OH group attached to benzene, making it a phenol for paracetamol. And we've got a CO and NH group present on it as well, which is the amide group. So for ibuprofen, we will write the functional group present are carboxylic group or carboxylic acid. And for paracetamol, the functional groups present are phenol and amide. Ibuprofen contains a chiral center that shows stereoisomerism. State what is meant by the term chiral center. A chiral carbon atom is one to which four different groups are attached via single covalent bonding. So four different groups are attached to the same carbon atom via a single covalent bond. Draw the two stereoisomers of ibuprofen. So the structure of ibuprofen where the chiral carbon atom present is this one being circled with a blue circle, because here we can see that four different groups are attached. Three groups are displayed in the skeletal formula, the fourth one being a hydrogen atom. And now we need to draw the two stereoisomers of ibuprofen. The chiral carbon atom has been shown. So we are going to draw a COOH group on this side. So on the other isomer, it will be present here. The CH3 group present here. On the other one, it will be present here. The hydrogen atom present above. Same position on the optical isomer. And then we have the benzene ring present on the remaining bond or the remaining position. And to this benzene ring, we've got the R group present, and we draw those as well. So these are the two stereoisomers or optical isomers, to be more precise, of ibuprofen. And we can also include a mirror in between showing that these are optical isomers, because the mirror indicates that they are non-superimposable mirror images of each other. And in this way, we have shown ibuprofen as being optically active or having chiral carbon atom. Question 3. Compound A can be produced from a plant hormone, and the structure is shown. Compound A shows optical and geometrical isomerism. Okay. On the structure of A above, draw a line through the bonds that give rise to geometrical isomerism. So geometrical isomerism is cis-trans isomerism, which can be shown by the double bonds present in the molecule, which are not part of a cyclic structure. So the line drawn through this carbon atom will show two geometric isomers, and the line drawn through here will show another two geometric isomers. So there are two bonds that can show geometric isomerism. Circle all the chiral carbon atoms. So in order for a carbon atom to be chiral, it needs to be attached to four different groups. So uh, on the ring, we don't have any chiral carbon atoms present except for the one on which the OH group is attached, because here we can see four different single bonded groups attached to the same carbon atom, making it chiral. And other than this, on the entire structure, there are no chiral carbon atoms present. So this is the only one. Next, give the names of the four functional groups present in A. So we start with the ketone, circling it here, ketone. Then we have the carbon atom that is chiral on which the OH group is present. So it is attached to three different R groups, making it a tertiary alcohol. Then we have the three double bonds present on the entire structure, showing the presence of the alkene functional group. And we've got a C double OH group also being circled right now, present on this molecule. So we also have the presence of a carboxylic acid group in the molecule. So these are the four functional groups present in A. A molecule of A has 17 carbon atoms. State the number of carbon atoms that are sp2, and sp3 hybridized. So in order to form sp2 hybrid carbon atoms, it needs to have a pi bond present, and for sp, it needs to have two pi bonds present. For sp3, no pi bonds present. So we start with the carbon atom with the double bond O group, the ketone group. So this is an sp2. So sp2. Then moving on to the double bond, we've got sp2 and sp2. Then moving on to the next double bond, sp2, sp2. Moving on to the next double bond, sp2, sp2. And moving on to the carboxylic acid carbon atom, we've got sp2. So in total, we've got 1, 2, 3, 4, 5, 6, 7, 8 sp2 carbon atoms. There are no sp carbon atoms present because there are no carbon atoms forming two pi bonds, so zero sp carbon atoms, and all the remaining carbon atoms will be sp3 carbon atoms. So labeling those, we would have 1, 2, 3, 4, 5, 6, 7, 8, and 9. We will have 9 carbon atoms that are sp3 hybridized. When A is reacted with an excess of hot concentrated manganate 7 ions, a mixture of three organic compounds is formed. X, Y, and Z. Suggest the structures of Y and Z. So X is the one with the larger part of the molecule. Y and Z are the ones where the blue lines have been drawn. So for Y, we've got three carbon atoms. So this would be two carbon atoms with a CH3 group on one of the carbon atoms, and the other end would have a C double OH group. So C double OH, and this would be CH3, but the bond is broken here. So this part, and this would be a ketone. So we would have a double bond O group here. This is the molecule that is formed between the two blue stripes. This is the remaining part of the molecule which is oxidized. So one end becomes a carboxyl group, the other end becomes a ketone group. Now we are going to look at the molecule that remains after the second strike. So we end up with CH3, CH2, then we have a C double bond O because it is bonded to another C double H group. So C double bond O, and then we have got a C double OH group present here. So these are the two molecules that are present. Now, in order to draw these again in a more straight chain structure, for the one on the left, we would have a C double OH bonded to a C double bond O bonded to CH3, and the one on the right would be C double OH bonded to C double bond O bonded to CH2 and CH3. Now, this is the molecule Z drawn properly, and the one on the left in red is the molecule of Y drawn properly. So these are the two products when A undergoes oxidation using hot concentrated manganate 7 ions. The third compound that is formed is the one with the cyclic structure in it, and that is the one that is not been asked here. Question 4. Abscisic acid C15H20O4 is a plant hormone, and the hormone is drawn over here. On the diagram of abscisic acid, use an asterisk to label each chiral carbon atom. And in order to look at the chiral carbon atoms, we need to have four different groups single bonded to a carbon atom. So if you look at the ring structure, we don't see any carbon atom that has four different groups attached other than the one with the OH attached to it. So this is a chiral carbon atom. And moving on along the molecule, we do not see any other carbon atoms with four different groups attached to it. So this carbon atom marked with an asterisk is the only one that is a chiral carbon, and because of this, abscisic acid will have two optical isomers present. Abscisic acid is reacted with an excess of NaBH4. NaBH4 is a mild reducing agent. Give the molecular formula of the organic product formed. So a mild reducing agent will have no effect on the COOH group, and it will have no effect on the tertiary alcohol group, the one that has been labeled with the asterisk, but it will reduce the ketone to a secondary alcohol, meaning the double bond O will be converted into single bond OH, which means that the formula will have addition of two hydrogen in it, and that's it, because one hydrogen will be the one that will be bonded to the oxygen atom in order to convert it into OH, and the other hydrogen will be attached to the carbon to which the oxygen atom is attached to. So there will be an increase of two hydrogen atoms and no other change in the molecular formula. So the new molecular formula would be C15H22O4. If abscisic acid is treated with an excess of hot concentrated acidified KMnO4, three different carbon-containing products are formed. Draw the skeletal formula of the carbon-containing product with the largest molecular mass. So the one with the largest molecular mass would be the one with the cyclic structure in it, and the bonds that will be broken would be the ones that are being drawn with a line passing through them, and the molecule that will be the largest one would be the one that is being encased in a blue box. So, in order to draw the skeletal formula for this compound, we will make the same structure as drawn, except for the double bond that gets broken. So, we end up with the double bond being broken, giving us a ketone group on the right carbon atom and a carboxylic group on the left carbon atom. So we have the molecule, the skeletal formula of the molecule drawn, except that the bond that is broken on the top will have the carbon atom being converted into a COOH group as well. So this is the structure of the product with the largest mass. Identify the carbon-containing product with the smallest molecular mass and explain how the product arises. So if we look at the third bond that is broken on the right, which has been labeled with a line, we end up with a molecule of oxalic acid. Oxalic acid is two carbon atoms, both of them being a COOH group. And since we are using hot concentrated KMnO4, this will undergo further oxidation to produce CO2 and H2O. So the one with the smallest molecular mass is CO2. So the answer here is CO2 is formed by oxidation, because oxalic acid is further oxidized into CO2 and H2O. So oxalic acid is one of the products formed on the oxidation of abscisic acid. So oxalic acid undergoes further oxidation to produce CO2, and CO2 is the one with the smallest molecular mass. Identify the third carbon containing product of this reaction by giving its displayed or structural formula. So that would be the part of the molecule between the two double bonds on the top right. So we end up with two carbon atoms. So we've got carbon atom bonded to a CH3 group, and this carbon atom converting into a ketone, and the one on the left is the carbon atom that will be converted into a COOH group. So this is the skeletal formula of the structure, and in order to make the mm, displayed formula, we will have COOH, then we will have a C double bond O group, and then we will have a CH3 group present. So this is the molecular displayed formula of the third product that is formed on the oxidation of abscisic acid with hot concentrated acidified KMnO4. Question 5. Calcitriol is a steroid hormone found in human blood. Give the number of primary, secondary, and tertiary alcohol groups in one molecule of calcitriol. So we have three OH groups present. Let's begin from the bottom left. This OH group is a secondary alcohol because it is attached to two R groups. The other OH is also a secondary alcohol attached to two R groups, and the OH on the top right is attached to three R groups, making it a tertiary alcohol. So we end up with zero primary alcohols, two secondary alcohols, and one tertiary alcohol. Give the number of chiral carbon atoms in one molecule of calcitriol. So in order to find the number of chiral carbon atoms, we have the first secondary alcohol as a chiral carbon atom. We have the second secondary alcohol as the chiral carbon atom. And moving on, we have this carbon atom as a chiral carbon, this carbon atom as a chiral carbon, this carbon atom as a chiral carbon, and this carbon atom as a chiral carbon. The one with the tertiary alcohol group attached to it is not a chiral carbon atom because it is attached to two CH3 groups, which are the same group, so it is not a chiral carbon. So in total, 1, 2, 3, 4, 5, 6. 6 chiral carbon atoms are present in one molecule of calcitriol. Calcitriol shows geometric isomerism. Give the number of geometrical isomers of calcitriol, including calcitriol. So, geometric isomerism will be shown by double bonds with the groups that are same on both ends. So, that would be the carbon atoms, the double bonded carbon atoms here and here. A blue line has been drawn through them. The third carbon atom will not be showing geometric isomerism because on its end carbon atom, terminal carbon atom, there will be two hydrogens attached to it, which eliminates it from showing geometric isomerism. So we end up with only two carbon atoms, or other two double bonds that are capable of showing geometric isomerism. So the number of geometrical isomers would be 2 power 2, because n the power is the number of number of double bonds that are capable of showing geometric isomerism. So this will give us 4 geometric isomers for calcitriol. A sample of calcitriol is treated with an excess of hot concentrated acidified potassium manganate 7. There are 3 different carbon containing products of this reaction. One of these 3 products, X, is shown. In addition to the product X shown, two other carbon-containing products are formed when a sample of calcitriol is treated with an excess of hot concentrated acidified potassium manganate 7. Of these two other carbon-containing products, identify the product with the smaller molecular mass. Explain how this product is formed. So we have the bonds that are broken would be 1, 2, and 3. And when this bond is broken, the third one, we end up with this part of the molecule being converted into HCHO, which is methanoic acid, which will be further oxidized to, this is methanol, which will be further oxidized to methanoic acid, which is further oxidized to CO2 and H2O. And CO2 will be the one with the smaller molecular mass. So explain how this product is formed. One of the double bonds that is oxidized forms methanol as an intermediate product, which is further oxidized to methanoic acid, which is further oxidized to CO2 and H2O. And this is how CO2 forms. So basically, we have written down the reaction path taken by the carbon atom that undergoes oxidation on reaction with hot concentrated acidified KMnO4, forming methanol, forming methanoic acid, and finally forming CO2. Of these two other carbon-containing products, identify the product with the larger molecular mass by drawing its skeletal formula in the space below. So we have seen one of the bonds forming CO2. The other bond, the bond that is broken in between, forms compound X, and the double bond at the top, when it is broken, results in the formation of the third product, and we need to draw its skeletal formula. So all we need to do is draw the skeletal formula as shown in the formula of calcitriol, with the double bond being broken, forming a ketone group. So the rest of the molecule remains the same. And all we do is complete the structure as seen in the diagram above. And this is the third molecule that is formed upon oxidation of calcitriol.